So yeah, so I'm Mahidhar Tatineni. As Cindy said, I lead the user services group here. So today I'll talk about basically code migration concepts and how you can do that on our Expanse supercomputer, but it applies to basically a lot of systems since the setup is similar on our other systems. So let me get going. Just a quick note about Complex. If you are new to this, it's a new SDSC program where we are basically trying to train people to cover non-programming skills to basically effectively use the computers, uh, things like parallel computing concepts, Linux tools, scripting, security, batch computing, and just in general, getting familiar with HPC and supercomputing systems and how to use them. So a quick outline of what I want to cover today. Basically, start with applications that are already available on systems, whether it's Expanse or other systems. And typically, these are managed via modules. So I'm going to go over how you can explore what's already on the system. And we also make available some optimized builds in Singularity containers. So I'm going to talk about that also. So that's kind of the easy button, right? Like if it's already on Expanse and we have an example, you get on and start using it. Then I'm going to go specifically into Python and R applications, and mainly because there are multiple ways to to use these applications, and we just want to go over the various approaches you can take. And then in the end, I'm going to talk about basically building applications from source code. This might be the case, say, for example, if you have a community code that needs a lot of dependencies that are available on Expanse and modules, but the code itself doesn't exist on Expanse and you're building it from source, I can go over some details on how to do that. And the last thing out there is a note about user-built containers. I'll briefly go over how that works and how you can do that. So let's start with the applications that are already on Expanse. So we've made available a large suite of libraries and applications on Expanse. I think number of packages is over 200 pretty easily, I think. This also includes some commercially licensed software like QChem and Abacus and Gaussian. And our primary approach for this is to make them available using environment modules. And if you're logged in on the system, the easiest way to find these applications is to use the module spider command. Especially if there are multiple versions and if they can be loaded in different ways, the spider command is very useful to kind of get info on the modules that you need and the sequence that you need to load them in so that you can actually get the environment you need. And as I said, some of them have been made available through containers, and I can give you some examples of that. So starting off, essentially, let's look at an example of how we can find applications via modules. So at this point, I'm going to switch to sharing my terminal so that we can actually walk through this, and then I can come back to the presentation, which sort of summarizes things. Let me see. So everyone can see my terminal, right?
Yes.
Okay. So yeah, if you're looking for a module, say the example that I have there is MATLAB. So you want to know what's available on the system. So if you do module spider MATLAB, it's going to give you information on the versions that are available. And you can see that we have 2020B, 22A, and 22B. And then if you want to pick a particular one, say you want to know how do I get MATLAB 2022B. then you'll see that there are two versions, and the reason why we have two versions is we actually have different stacks for GPUs and CPUs on Expanse because they're different kinds of processors. But if you do a module spider, a particular version, so let me get that. That's taking longer than I thought it would. Yeah, so now you'll see that you have to load the GPU module. So I picked up the GPU version essentially. So you load the GPU version, and then it actually gives you some description on uh, what kind of package it is and everything like that. Now that comes from the module itself. So now if you want to say do module load CPU or to see the other version. So you can say module load MATLAB. So as you can see, it picked up the other version because I had the CPU stack loaded. And at this point, if I do rich MATLAB, you can see that MATLAB is in my path. So essentially, uh, just loading these two things has given me access to MATLAB, and you can run MATLAB. And of course, we run MATLAB both through the batch queue and through an interactive setup, but I just wanted to show you one example of this. So that's MATLAB. So let me go back to the presentation, which seems to have, oh, it's out here. Okay. So going back to the presentation, so we figured out how to get a particular package and walk through that. Now things can get a little more complicated if it's a library that depends on, say, more than just whether you're on a CPU node or a GPU node. It might depend on the compiler. It might depend on the MPI that you are using if the package is MPI compatible. So one example of this is FFTW. So if you do module spider FFTW, so if I go back to my, and I can show you how that will show up. So you can see that if I pick a particular version, then you can see now that I have to load the CPU version, CPU stack, the GCC compiler, the MPI compiler, and then you load the FFTW. And so the way it would go is basically you do a module reset, load the CPU stack, load the GCC compiler and mVAPage, and then you load that. And whenever you do a module show, you can actually see what the module is doing to your environment. So let me go back and show you that on this on the share screen. If I go back to that, we'll do a module spider FFTW, and we can see that there are several possible matches. So I'm going to do module spider 3.10. And you can see there are so many different versions, and you might be wondering why. Is because this is the combination of all our compilers and MPI versions that we have. So it's a little messy, but you can find. So if I do this, now you can see that this is actually a version that is for the GPU and Intel. So you can see that. So if you do a module load, I'm going to do a reset. Sorry. And let me do that spider again and do a module load on both the GPU and CPU stack. And then if you do a module load FFTW, you get that version of FFTW that was built for actually a GPU node. Now, if you do module show FFTW, you'll see that it actually sets a bunch of environment variables. If you scroll down, it's going to prepend to the LD library path, which is the dynamic library path, the path. So any binaries that exist, it's going to add to the man path, add to the CMake path, and so on. And the one thing at the end that I want to mention is that we, for all our modules, set like a home location. And when I talk about compiling from source, you'll see why this is useful, because you need to know where the package is so that you can include and link libraries correctly. But just keep that in mind for now, that you can actually get a lot of info by doing a module show. And you can also, when you load the module, all of this gets set. So you have all these variables set essentially. So let's go back to the presentation. So as I mentioned, basically the spider is giving you the loading information. We just walked through how to pick the combination of dependencies to load before you actually load the module that you need. So that's where the spider is useful also. One thing I want to mention for Expanse, and this is not going to be true of all machines, or it might be true on other machines, but basically we have separate different CPU types on the GPU nodes and the CPU nodes. So on our bulk of the system, we have AMD ROM processors, and those are all the compute and shared partitions that you see on Expanse. And on the rest, the GPU nodes, we have Intel processors. And you cannot mix something that's compiled for the GPU stack on the CPU stack and vice versa. And this is because the processors support different AVX versions, for example, and different basically binary levels. So like the Intel processors support AVX 512. So if you build with that, you will pick up those AVX 512 flags from our modules. And then if you try to run that on an AMD machine, which only supports AVX 256, you're going to have problems. So key thing to keep in mind is do not mix the two. So, and this typically happens because people look at module spider and say, oh, I need this package, but it's not in the CPU stack, it's in the GPU stack. So they try to mix the two, and then it doesn't work. So if you do see something like that, it's better to let us know, or try to compile whatever is the missing thing yourself instead of trying to mix the two stacks, basically. So one other thing is we have a lot of application usage examples in CM shared examples SDSC. So that's a good place to go look, because if you have confusion about what modules need to be loaded for a particular package and so on, the example script will have the loads. So that's a good place to essentially start. So let me take a quick look at the chart and see. Okay. Um, so I think couple of questions there. So I think uh, Johnny, you mentioned were asking what it means by prepend path. It basically means like the dynamic library path or the path might already exist with a lot of variables, a lot of paths in it. What this will do is uh, basically separate out the I mean, add this extra path at the start of the variable setup, so that it's picked up first. So for example, if I load an FFT module, the binary path will have that FFT location first, so that it picks up whatever is in that first and then goes on. A similar thing with the library path. And in terms of, is there a way to get options about how the particular modules were built? I think yes. The short answer is yes. Actually, maybe I can just show it to you. Let me. Because all of our modules are built using SPAC, we actually end up having the SPAC config info in the module, in the installed directories. So let me do that. Let me show you. So since we already did the uh, FFT install, sorry, load, I'm going to show it to you here. So if you go there, there is a .spac directory in that location. And if you look at the config arguments, they're all there actually. So you can get details. This may be too much detail, but it's all there. Sorry, I think the build options are out here. So let's see, or actually here. So you can see the config options out here. And since it was GPU, it actually picked up the AVX512 automatically. So you can see that. So anyway, you can find that info. Typically, as an end user, if you're just using the package, you may not need that info, but it's good to know, especially if you're trying to replicate the configure with the same kind of options. So yeah. So let me stop sharing that and go back to the um, so I think there was an example question about asking. Oh, yeah, actually, I'm going to show you one of those in the presentation itself. So let me just continue with the presentation. Oh, let's see. So that was everything that's installed via modules, available via modules. This is our stack is based on a spec-based install, which generates those modules automatically, actually. So now I'm going to look at some that are available via Singularity containers. Now, all our containers on Expanse are in CM shared apps containers. And we've chosen the container route for a few of these because it's a lot easier to manage all the complicated dependencies together. So some examples are basically TensorFlow, PyTorch, AlphaFold, ParaView, Visit, all packages that are available through containers. One other thing I want to note is that we do have the extreme scale scientific software stack, E4S stack, available via container. And I have a reference there, which basically this comes out of the exascale computing project. And they have a nice combination of scientific libraries and math libraries and packages that are used in HPC very routinely, uh, all bundled together in a nice container with which you can use. So that's also available there. For example, you can run. They have a ParaView install in their own container too. Uh, and we have Singularity definition files if you want to kind of rebuild or change these containers in some way. So that's another option essentially. And this is something Marty maintains, and I have the link down there. So I think someone asked about the example directory, one of the examples. Well, this is one of the examples for it that uses Singularity, but it essentially has info on how you load the Singularity module, for example. So if you do a module reset, module load Singularity Pro, that puts Singularity in your path, and then you can use the container. So in this case, we are running on a GPU node. We are asking for one GPU, and this is a standard benchmark that we are running. And essentially, we do Singularity exec, and we are bind mounting the directories that we want. So when you're running using containers, you have to bind in the directories that you're going to use. So in this example, we're binding in /expanse, which will cover pretty much the Lustre file systems and the Lustre projects and so on. And we are also binding in /scratch, which basically is the node local scratch directory. So you can bind both of those in. And then the --NV essentially pulls in the NVIDIA driver info and everything, and the setup. So, and then we have the PyTorch container, which has essentially all the required packages for running PyTorch. And then we are running our Python script. So, and this, by the way, these containers we are maintaining, but if you have an existing, say your group already has an existing Docker container, you can easily convert that to Singularity and run it on our system. So, so the containerized options are pretty portable. So if you know, if you have other solutions, you can definitely use them. So basically that covers everything that already exists on Expanse in some way that uh, we are basically maintaining those packages and keep updating the containers when we update the drivers. And for example, if the NVIDIA driver updates, or if our InfiniBand driver, which is a network driver, updates, we'll go update the containers. Next, I'm going to go into Python-based applications and libraries. So there are multiple options here. First thing is we do have some in modules. It's not a big coverage, but several applications and libraries are already, Python applications are in modules. For example, Matplotlib or NumPy or SciPy. So if you want to use those, you can do exactly what we did with the modules before, basically, because this is part of the module stack. So you do module spider on a particular package and get more info. Some of these modules are dependent on MPI, like the PySCF and the MPI for Py, for example. So if all the packages you need, like all the Python packages you need are available in our modules, you can just use a modules-based approach and you don't need to do anything else. But a lot of times you'll find that either the package we have is not the right version, or you want something specific for your own install that doesn't exist in our package. Then I would suggest going the Miniconda route or the Singularity approach. Either way is fine. If you have a container, that's probably quicker. But if you need to build something from scratch, then maybe just get a Miniconda install. And I'm going to talk about the Miniconda 3 side of things. So basically, uh, most of our users, what we see is end up with either a Conda install or a Singularity approach. But the key thing to keep in mind is that you have to stick to one particular approach. You can't mix things between all of these. So you can't say, oh, I'm going to load like a Python module and an MPI module from Expanse and then go get a container and use it. With that, it won't work. Or if you mix it with a Conda install, it won't work. It's going to cause kinds of conflicts and unexpected results. So typically, we strongly suggest not combining the two. So installs using Miniconda. So yeah, if what we have in our modules doesn't cover, you can go the Miniconda route, especially if it's custom installs with both Python and non-Python dependencies. So the key is to install this in your home directory. Don't install Miniconda into Lustre. This causes a lot of problems because basically the Conda installs have tens of thousands of files. And every time you load or initiate something in Conda, it's going to walk a lot of the files and cause a lot of metadata loads. So that causes issues on the Lustre file system. So the home directory is a lot better with dealing with this. So you can install that into the home directory. The other thing to keep in mind with conda installs is to make sure that the packages you're picking are compatible with our drivers. Specifically, this pertains to GPU installs. For example, on Expanse right now, our driver version is 5.1, sorry, it should be 525.85.12, and that supports CUDA version of 12. So if you just blindly go get the latest version of the conda version of a particular software, and maybe it needs CUDA 12.3, and that's probably not going to work because the driver is not compatible. So whenever you're doing this, make sure you install a version that's compatible with our driver. And I'm showing you an example here of how to get basically going with Miniconda installs. We typically suggest doing any major installs or any major compiles on a compute node or a GPU node instead of trying to do the installs on the login node, because they can tend to get overloaded. So here I just got myself access to a GPU node and just had a Miniconda install script and then continued that installation process. So the reason I was showing you this particular thing on a GPU is to show you how you can pick a particular version. So for example, if you do a conda search on CUDA, you can see different versions and say you pick a particular thing like 11.6, which will be compatible with our driver. But you should keep that in mind. So so that's a consideration to always have, especially if you're installing PyTorch or TensorFlow, and that has the dependency of CUDA behind it. That's going to be an issue if you don't match the driver. So the next thing I want to talk about is MPI for Pi, and this is one where you really have to be careful. The MPI for Pi install needs to be consistent with the MPI being used. So we have a system install of MPI for Pi under the Python list. So those will obviously be built with our MPI, so that should be okay. But where you get into tricky situations is if you do a Miniconda install of MPI for Pi, what it will do is install an MPitch version within Miniconda. So your MPI will be within Miniconda, and it will also install the MPI for Pi based on that. Now, that will work fine for single node cases, but a multi-node case, you'll have trouble because it's most likely going to go over the Ethernet instead of using the faster InfiniBand network, and you can run into trouble with performance and timeouts and things like that if things are not optimal. So use the system installed versions if you can, but if you absolutely need to combine it with the Miniconda, the one approach that has worked is to combine that by building MPI for Pi from source, but with the system MPI loaded, so that it doesn't automatically install MPitch. This is a little tricky. You can contact us if you go down this route because there are performance implications, and I think Marty may have mentioned this in the oops. Let's see. Yeah, I think Marty mentioned it in the multi-node thing. Yeah. So that's the Python aspect of it. And I didn't talk about a containerized option for Python, but I'll show it to you for the R-based applications, and you can see you can do a similar thing for Python, basically. So there might be a question, I think. Yeah. So in terms of R has a similar setup. Basically, we have Are applications and libraries available via modules? There are a lot of the standard ones like Biobase and do parallel and ggplot, etc., are already there. But again, it can get complicated really quickly if you want other R packages installed, and if further installs are needed, again, you just like Python, it's best to go through Miniconda 3 or Singularity approach. And the same warning about mixing between modules and ones from conda container applies. They'll fail if you don't uh, if you mix them. So here I'm going to actually show you an example of using R via Singularity. So this is actually a user request that had come in. And basically they said, oh, there's a Docker image we use all the time. So what can we do? So what I suggested doing is to basically convert that to a Singularity image. So what I've done here is uh, uh, basically gotten interactive access to a compute node. And the reason I'm doing this on a compute node is because when you build a Singularity image, it creates a lot of temporary files. And the default is to use /temp. And on the login nodes, the /temp is really small. So you're going to run out of space and then get in trouble. So it's better to get interactive access to a compute node, set your temporary directory, and we are doing this automatically now, so you can actually skip that export step. But basically pointing it to the local NVMe, which is a lot larger, load the Singularity, and then actually building a Singularity image from a Docker image is quite simple. So for example, here I was building a code called xsub. This is a container for xsub. So I did a Singularity build, xsub.sif, that's the name of the container, Singularity controller, and then pointed to the Docker image. And it's going to go through a huge build process, probably take a few minutes. And in the end, it's going to create this sif file. Now, not that you just need to do this once, right? You can keep this container file around, and then for all your jobs, you can continue using the same container. So, uh, uh, so that's a quickest way to use a Docker container. Just convert it, and then you can start using it. So once you have the container using the, yeah, excuse me. Using it via Singularity is just like the TensorFlow and the PyTorch example I showed you. So I'm just resetting, loading the Singularity module. So this is running in the shared partition on a compute node. So I'm doing Singularity, and this particular uh, container actually just takes arguments and runs. So you can basically bind in the uh, uh, directories that you want, like the output location, the input location, because it actually needs some reference data at a particular location in the container. So that's what I'm doing here. So I'm basically bind mounting it to the location, and then just using it with the container with whatever the input path, basically with the input file is. So essentially, uh, this package has a bunch of dependencies, a bunch of things that are all taken care of within the container, so we don't have to worry about it. And we just converted it and used it. So it's a pretty quick way to get going if you already have something containerized. So, so I mean, I can actually also show you an example of, let me go back to the, terminal. One. So if you go to our CM shared examples, I think I have a review example that shows you how to use the E4S container, because that's another one that is yeah, so this is an example of a package, again, E4S, the maintainers of E4S, there's a big effort behind it, and they have a lot of nice optimized builds in the containers. So this was one example where I basically converted that container and just used it. And this one actually even has a CUDA version that it uses, and you can pick the newer version if you want. But basically, again, running through that, it's actually got modules within the containers just to confuse you further, because they have a whole stack in it. So they actually set up a module setup within that, but then you can essentially run that. And this one actually has an MPI. And the MPI launcher, I'm using a fork option here because I want to just stick it to one single node. And so it's spinning up essentially ParaView server and listens to basically connections so that you can use ParaView through the container and do your analysis. So that's a good example of going further with it. Thanks, Bob. I think there's a question on the memory value. Back to the presentation. So screen. So the next thing I want to talk about is building and installing applications from source code. Now, this used to be the case, like a decade ago, you would probably all be doing this, but now things have changed quite a bit. But building from source. So I think there was a question about configure scripts and so on. So yeah, some applications have configure scripts that pick up dependencies based on whatever environment variables and modules you have loaded, right? One good example is Quantum Espresso, and this is a build script that I had have as an example. Well, in CM shared examples, basically. So this is using a compiler, GCC compiler, an OpenMPI. So that's an MPI implementation. Then it needs a LAPACK and a ScalePack library, um, uh, and it needs FFTW. So it basically, we are loading all the modules for it, right? Then you need compiler flags. So you basically set particular compiler flags. Since we loaded the GCC compiler, I'm setting the C compiler to GCC, the C++ to G++, and so on. And there are all these optimized flags, right? So I'm using O3 optimization, and core-avx2 essentially gives you AVX2 instructions, which is what the AMD ROM needs. Now here is where things get a little interesting, because sometimes the configures are good enough to pick up all the libraries. Sometimes you have to point them explicitly. So in this case, we are actually pointing them explicitly out into the thing. So and the configure for Quantum Espresso actually looks for these variables. So that's what is useful to know. So any package that has a configure, you can do a configure -- help, and it's going to tell you all the variables that it looks for and things like that. So you can set all those things. So in general, here basically I'm setting the FFT location. So remember I mentioned that the home location of the package gets set in the module. And that's what becomes useful now because the library is usually in that location/lib. So we can just use the variable instead of that huge long path that we saw for the location. And then link in the FFTW library. Similar thing with include files. Put in the include files and the blast locations and the LEPAC locations and so on. Now, one thing to mention is that Quantum Espresso has all these is looking for all these flags. Not all packages will be looking for all these things. So, for example, if it's generically looking for include and library locations, what you can do is for the include files, you should add to the CPP flags. Typically, all configures look at CPP flags for include. And for the libraries, all configures will look for LD flags. So you can set all the libraries in the LD flags. That way, the configure will automatically pick up all the locations. And then you just run the configure because we've set all these variables, it's going to pick up all the locations that come from the modules. So that's one way of some packages get installed. Let me see, there were some questions, so I should probably, hold on. Being answered, so I'm going to continue a little bit. So that's one way of looking at it, but there are packages where maybe you don't have a configure and you just have a make file. So this is an example of a package where there's only a make file. So then, as you can see, they had a location for libraries, so lib flags and include flags. So, and if you look further down, they actually, when they compile, they have the include and library flags in the make definitions. So all you need to do is essentially add the library location. So here, now it's a little ugly. You can see the whole long path. And you can use the variable, home variable also instead of this. But here I'm using basically the whole path and doing a dash L pointing to where these libraries are located. So for example, OpenBLAS is located in that OpenBLAS install directories lib subdirectory, and then FFTW3 library is located in similarly with the FFTW location. And same thing goes for include flag. So you change those two, and then the make file will work because it's going to pick up all the locations. So this is if you're starting from scratch and essentially compiling everything from scratch. And again, if you run into trouble, you should let us know. One thing to keep in mind again is if you're doing an MPI based install and you're loading multiple packages, make sure that you're using the package with a consistent set of compiler and MPI locations. That is, don't get the FFTW with Intel MPI and then go find some other package like Scale-Pack that was built with OpenMPI. It's not going to work. So you should have a consistent module load. Now, if you're using modules and you try to load inconsistent things, that will get pointed out to you. So it's going to be okay, but if you hard code the paths, then there's a chance that you'll make a mistake and essentially have conflicting things. So things to keep in mind, basically. So maybe I should actually stop and show you how that will look on the terminal. So I'm going to do a reset. I'm going to load Intel. I'm going to load OpenMPI of version, say 4.3. So now I have a compiler loaded and an MPI loaded. So module li just lists what's loaded. So now if you do a module AV, it's actually going to tell you all the packages that combine these two locations. So for example, now if your package needs FFTW, HDF5, and maybe it needs NetCDF. So you should load these particular combinations because that's what's available under this Intel and OpenMPI combination. So for example, if I do module load FFTW, it's going to pick up the one that's got the same compiler, so you can see the version there. So make sure you do that, and so see now it's not letting me load the HDF5 without a version number, so that's what you need. So now I have FFTW and HDF5, and if I load the NetCDF Photon, say, I get that also. So, and notice I loaded the Fortran one, and it actually loaded the NetCDF-C also. It's because it's a dependency, so you need both of them. So that gives you the full combination of things now that's consistent with this particular compiler set. So now you can, if you echo the locations, you'll see uh, uh, where all these packages are located. Like so, and if I do a /lib, oh sorry, I should. So if I look for things in that lib directory, you can see that the libhdf5.a exists there. So when you link it in, you'll have that. And typically HDF5 will also have this HL library that needs to be linked in and so on. So the module is setting all those things. So but your configure and your uh, uh, and your make file may not pick these up automatically. So say you load a bunch of modules that you know you need, and then you do a make and it says, oh, I can't find your FFTW. Most likely that means it's not detecting what's loaded. You need to explicitly go put in the paths in your make file. So that's the thing to keep in mind. All right, let's get back to our presentation. So that's basically building from source. So few more things to think about when you're building from source. If you're building a GPU code, please compile on the GPU node, especially on Expanse, because as I said, the CPU that's on the GPU node is different from the ones that are on the login node. So you'll end up building something that won't work if you build it on the login node. The other thing is the login nodes don't have any GPUs. So like if you're trying to link in a CUDA library that's on the system, that's not going to show up on the login node because there are no GPUs. So either way, the only way to make this work is to run on a GPU. I mean, even the compile on a GPU node if you're running on GPUs. As I mentioned already, don't mix installs from GPU and CPU. Now, if you have a CPU code that doesn't have an intensive compile, you can compile that on the login node because the processor matches the CPU nodes. One other node, often you'll see if you're building from source, packages like BLAS and LEPAC and ScalePack are needed. And there are several options for this. So OpenBLAS will cover both BLAS and LEPAC. We have a ScalePack installation. Separately, we have an MKL. This is the Intel math kernel libraries that are also on the system that also provide all of these. And then we have the AMD optimized libraries, the AOCL libraries that are also available. And if your question is, which one should I pick? It's actually very dependent on the application is what we found. Like most applications do well with OpenBLAS and MKL. but in some cases, the AMD optimized ones are faster, so you have to maybe try a few and see which is more optimal for your particular application. Another thing to keep in mind is all our libraries, since we are SPAC installing in a different location and they're going to be in non-standard location. And the reason I mentioned this is sometimes there will be some software packages which will say, oh, just yum install or apt-get install this library. And they expect it to be there in /user include or /user lib 64. And we don't have them there. So if you run into those sort of errors, make sure you use like configure or CMake or make file options to point the build scripts to the right locations. Uh, because it still works. It's just that you need to make the install setup aware of where the location is. Don't try to do a sudo install because none of you will have sudo. So that's a thing to keep in mind. And then last thing is the Intel compilers. You might be wondering why we have Intel compilers. It's because they actually do better on some applications, not all, but some of the applications, the Intel compilers do better than GCC, even on the AMD nodes. So if you do use the Intel compilers, do not use the -x host switch. It's because it detects the processor wrong and then ends up giving you a really poor performing code. So switch to using the core AVX2 flag and it will all be fine. So let me see if there are some more questions. All right, I think I see Marty's answered the thing. So, okay. So basically, that is the building from source part. And the last thing I want to go into is user built containers. So I showed you how you can build a Singularity container from a Docker container. That's pretty quick and easy to do. Uh, uh, and that's nice if it works for you, especially if it's a single node case, it'll probably work fine and you can use that. But there are cases where you have MPI installs where the same issue that I was talking about with conda also shows up with containers, is that the MPI in the container should match the external MPI version. Although the E4S stack actually has a way to deal with this, but for most cases, you kind of have to do MPI in the container matching the external MPI version. So that means you have to make sure the InfiniBand drivers, which are the network cards in the on our system, are basically installed in the container. So we have example definition files. The link that I had to Marty's um, repo has basically definition files with the right drivers and everything. So if you are building a container that needs with a package that needs MPI, just make sure you have the IB drivers and then build the MPI within the container using that driver. And then you can do the rest of it normally. For GPU installs, similar thing, make sure that the packages you install are compatible with the drivers. So basically, again, if you get the latest and greatest container from NVIDIA and it needs CUDA 12.7 and you have, a driver that can only support 12, it's probably going to fail. So make sure whatever you're getting is compatible with our driver. Now, if you're building from scratch from a definition file, and I'll give you an example of a definition file in the next slide, but you need root access and you typically cannot do that on Expanse. But the good thing with containers is it really doesn't matter where you build. So you can go build them on your laptop or a cloud resource. For example, if you have access to Jetstream on Access, you can use that. Uh, uh, and once you have a container built, you can copy it over to Expanse and run using that. And Marty had a Summer Institute presentation last year with a lot more info. So you can go to that GitHub site. There's a PDF with the slides that you can look at. So just as a kind of info, basically this is a sample definition file, like on how what you can do within the container, basically. So this is the definition file that will be used to build a container that then can be run on Expanse. So this is a container that Marty had for basically using CentOS and mVapage. One thing to remember is that when you're using containers, you can have a different OS version. So for example, you could have an Ubuntu container that will run on Expanse that's actually running Rocky Linux, because as long as the drivers are compatible and the kernels are compatible, or at least you're not using some kernel features that are not existent on our system, it should be okay. But for the most part, you can build anywhere and run on Expanse. So here, basically, what Marty is doing is actually installing a lot of the InfiniBand drivers, and then he's actually building mVapage based on these drivers. So this is what I meant by make sure your MPI is compatible. So once you do that, the MPI that gets installed in the package will be compatible with our MPI, and then the rest of the packages that you build on top of that will be totally compatible and actually get good performance over IB. So that's the thing to keep in mind. And again, a lot of times, you don't have to go this far. So first check if things are already on the system or can be done in a different way, easier way, before you go down the route of building a container from scratch. But sometimes there is no choice and you have to do it, and then we can definitely help, and it's useful to have this kind of approach. So so that's kind of the quick overview of code migration and all the issues that are involved. We have a lot of training resources. So this is a more general thing, the training page, and you can look at our user guides for some info. And of course, you can contact us if there are any other questions. So I'll finish up. I think I'm right on the hour, so I'll finish up with basically just some conclusions. So as you saw, there's lots of options to get applications working on Expanse. First, easiest thing is to check if it's already there, either via modules or Singularity. Look at our examples directory and ask us before you go down the route of a tedious install. But if it's already there, that's the quickest one. The next thing is to go down the mini conda route or using containers. This is really probably the way to go for R and Python, just because they tend to have a lot of dependencies that are really difficult to install from source all the time. So it's a lot easier if you can have a baseline conda install or a container that already has all those included. Another thing to keep in mind is don't mix the installations. That is, don't take a conda install and try to use modules from somewhere else on the system. That's not going to work. Similar thing with containers. If you are in a container, use everything in the container. Don't try to mix something from outside the container into the container. We saw how we can use Docker images by just converting them to a Singularity image. And then the last thing is to build everything from definition files. So I will stop there and see if you have any more questions. I think some questions were being answered. Yeah, Marty had a good note there. We are kind of in a transition with the base containers, so do contact us if you're going the route of building from scratch.